Hey everybody, this is Larry. This is day 19 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this farm. And today and everything in between. Ran a couple of miles today, not that much. That's just all my training. Yesterday I did my cleans though. Like an Olympic clean. And man, my shoulders are sore right now, or my traps. So we'll see how that goes. Anyway, let's see. Looks like a classic problem, classical problem. But with 2D thing, we turn the volume, it can, or water can trap up the rain. Okay. That is interesting, I think the idea behind these problems is try to figure out the invariance, right? And invariant is, of course, something that I talk about a lot, and it is just the idea of things that don't change. Sometimes you could just think about them as properties of the system that don't change, even if you do random things to it, right? I want to say, at the very least, if you look at the four surrounding thing, it has to be. I guess that's not true. I was going to say that. Can you do simulation, right? Yeah, I mean, I mean, the height map is not that high, so we can do some stuff, but definitely you can do simulation with this farm, but I'm just trying to think whether there's a better way of doing it. I am doing this live in case you're watching it and think that it's just a explanation. If you're looking for those videos where they only tell you the solution and you feel smart, but you don't, I mean, that's fine, then, go for it. Watch those videos. You don't have to let me know about it. Here, I am actually trying to solve the problem as best as I can, and today we have a hard one. And though I know that a lot of people have this one memorized for whatever reason, I do not. I don't memorize problems, and sometimes I do remember them, but I don't memorize them. So I don't, especially these, I don't know. I would say that if you're a video game person, if you make video games, that is, there are definitely, a lot of these ad hoc, weird, grid-y problems to do. The first thing I was going to say was that, you look at the four adjacent side, and then, it'll kind of give you the, like, if you add a water here, it would just go somewhere else, right? But like I said, that might take a long time, especially, so can I do a little bit better? Like these visualizations are not super good, but here, if you look at this one, right, from the top down, maybe that's a little bit better, really. And the idea is that there is that one thing in the middle, that one grid in the middle, which of course has a different height. And I'm just trying to think about how to, just honestly, how to handle it, right? I mean, I guess, one idea that I have is, at the very least, start with the smallest number, right? And then the idea then is just boundary founding. But the problem is that could easily be n squared. And I don't mean n squared as in like c squared or r squared. I mean n squared as in r times c squared, right? So that could be quadratic if, or at least the number of distinct heights, because you can just do, like, you can imagine a variation that is like, 1, 2, 3, 4, 5, 6, 7, 8, and then if you just do 1, you update the 1 to 2, and then now you do the 2, you update the 2s to 3, and then dot dot dot. That's going to be very easy and square. And of course, I'm doing this in one dimension, and just to give you an example, and of course it's not a bow or whatever, but you can imagine that out, right? But that idea, I think, has some merit to it, in that like when we start at the 2, then we look around and see what is the biggest or what is the lowest word that we can go into. But we have to be a little bit careful, right? I don't even know necessarily how to do that, honestly. Because you just go, okay, can you go? Like if this is 4, then there's a path from here to outside, which is not great. If this is 3, then there is no path to go outside, right? But if you do it for every cell and you do a binary search or something like that, that's going to be too slow, right? Also, I want to say before I kind of keep going is that, if you look, sometimes you're tempted, for me, I never really care about this, but I think sometimes people comment on it about the acceptance rate and all these things. But the truth is, a lot of people memorize these things. So like, especially the earlier problems where they are well-known problems. I think this is I wouldn't say it's a well-known problem, but it's well-known of problem. I know of it, but clearly today I'm just not really seeing it, even though it is a classic problem. But why am I so bad today? I guess the first thing that I want to do is what happens. Maybe to simplify it a little bit. What happens if this is one dimension, right? Let's say we have this. Then what does this mean? This means that from the left direction, almost like you have a 2. You can go to, this could goes to 3, and then here. Now that it has another 3, then it has to end, right? Something like that. So you can play around with that idea. Though I don't know how to extend it to 2D. Man, I can't get the simulation idea out of my head, but it definitely is not the way to go. Though it would be very interesting. Like at every cell, you just give one to its neighbor or something funky. But okay, maybe I have to think about the problem in reverse, right? So if the problem in reverse is reaching from the outside, right? What is the... Maybe reaching from the outside, we go, okay, 1. What are the cells that we can reach with 1? Right? 2. What are the cells that we can reach with 2 from the outside? And then 3 and 4 and then so forth. But that's still, I mean, that's a fine idea, because then at some point when you hit 4, then now you can actually hit these cells, and you're like, oh, okay, well, that means that, or even 3, maybe, depending on how you want to code it, you can hit these cells and they're updated and they're all 3s, right? And it's the first time these gets hit. But yeah, the reason why I'm struggling so much is what I said at the beginning of the video, which is what I said about the invariant. I'm not really seeing the invariant, or maybe a property or observation. I'm missing something today. maybe all the time, I don't know. But let me keep hydrating. Maybe that's what I need. Well, I guess that is the idea, right? In a way, like from here, what is the shortest path, if you will, to get to the outside, right? And the shortest path is going to be 3. Yeah. So then that means that this can be 3. So we can do it for every cell, but again, that's going to be n squared. But maybe we can reuse some of this idea, right? And instead of processing it in that way, of lowest to highest, maybe we can process from highest to lowest. Here, we just process the 3. What's the lowest cost to go outside? Well, 3 is enough, so this is going to be 0. 2, the lowest is going to be 3. You go all the way around, right? I think my issue is that it's still a little bit wonky for me, because I don't know how to handle infinite loops per se. Like, for example, if this, like this 2 goes to this 2 and go back, then how do you handle it, right? And you could say that maybe we could just go to the other ways, but then what if this is like a 5 and this is a 5? Then now you kind of lied about it taking 5, because technically this 2 is the easiest way, but then you want to save operations, and this 2, right? Like, how do you... how do you do it that way? But I guess the answer is, again, going back to what we said earlier, is doing it in reverse, right? In some way. I have to figure out how to do it. I don't know how to do it, but doing it in reverse of outside going in, then now it is outside going in where the cost is the path of the max element. So then here, this 3, is it though? But that's still awkwardly phrased. I don't think that's quite right, because then you could say like, oh, this 5 is the max element, so 5 goes to 3, and then you snake around, right? So you have to kind of be a little bit or a lot careful. How do I mean, I think I have the idea. I just don't know how to turn this into essentially I want this to be a DAG instead of a graph with cycles. Right? Because in this case, in this modified case, we want to do this 2 first so that this 2 can be based off this, right? But maybe, like I said, you can do it maybe in reverse from outside, but even then there can be weird edge cases, so that's why I'm kind of struggling a little bit, right? Let's say we handle the 5s. Right. Because you don't want to update with the 5s, you don't want to update just the entire thing, and then and then the 3 has to update the entire grid again, then it doesn't really it doesn't really work. Well, it works as n squared. So I feel like we have n squared, but maybe that's fast enough. I don't know. 40,000 square now. I don't think 40,000 square is fast enough. Man, today I am struggling. Unless I have to do max flow. But 40,000 is a lot of element for max flow though. How do I handle this? Each cell. So we do have the idea. It's just that it's too slow and we'll figure out. Which is that for each cell we want to find the shortest path to go to outside, where the shortest path or the cost of the shortest path is the max element, and we want to minimize that, right, on the path. But the thing is that, and if you do it that way naively, it's going to be n squared, which is too slow because n is 40,000. Right, it's just too slow. So then the question is, can we do a little bit better? And the way that I want to do is that, well, we use energy or answer, right? Energy. We use answer, and therefore we get it down to O of n. But that's the problem, is that I don't know how to do it in a correct ordering, right? Is there a way to do an ordering? Man, I really don't know this one. Should have taken a nap first. It's not really a binary search because you might have different connected grids and different heights, right? Can I reword it in some way? Okay, let's say we go from the highest number first, so we start at 5. What do we update? Right. In the same way that we have the 3, what do we update, really? I mean, okay, maybe we update the 2s. But then how do we do that in a way that propagates but also not propagate? Like I said, I'm missing an invariant. I don't know how to do this quite yet. Can we take advantage of this? What's that? 20,000? 20,000 is still kind of a little bit high. Especially 20,000 times 40,000. I guess that's a little bit better, but it's still not great. I mean, yeah. Wow, sorry friends. Now you're just watching me like sitting here. We don't know. Is this the shortest path? It should be, but... I mean, there are some things you can say, like all the 2s that are connected, we can just do them together. Is that enough to get rid of the cycle? I'm just right now. I'm just trying to come up with a counter case, because the thing is that with this heuristics is that you do have to. I mean, you don't have to. You can prove with AC, but I'm trying to prove that maybe that is true. And of course, you only need to do it with the interior ones, because the ones on the edge will never need to do it. So then, okay, what's your strategy there then? You get the answers with these twos, and then can you have two intersecting things? I guess not, because it's a two-dimensional grid. And what I mean by that is, could I have something like I don't know, two. I was thinking like, okay, if you think about like something like that, and then you have like a 3, but you can't really do it because, I mean, you can interlock some of it, but it should still be okay, because you cannot mutually be inside one thing. So is that it then? You do them in reverse order. You do the 3. The 3 gets lowest cost, and now the 2s. But that's still, I think my problem is that I still cannot show that this is an n square, because once you have something like this, or just even more complicated in general, then what, right? Like, so for each cell, if you want to do a binary search, how would that look? You want to get the lowest thing that doesn't go outside. But for each cell, and in theory, if you do a foot fill on that, that should get the whole component. Whole component. I'm just thinking through different cases in my head, whether that really works. I don't know how to do it. Is it just me being lazy and tired? Maybe. But today I am not. I mean, the formation is okay. The optimization, not so much. Yeah, I have an idea, but I just can't prove it. It is kind of DPE, but no, because by definition, then. But you're not doing it in that order. I'm just thinking of the case of like, okay, well, I mean, this is gonna be a 1D version, but you have like 1, 2, 3, 4, and and I don't know, whatever, right? Something like that. Then now, if we do it in high to low order, this 4 is going to get a 5, that's fine, but this 4, what does it do? well, it goes to the left, find that it has nothing, but in doing so, then now you have this n square thing going to the left, where it's like, okay, yeah, we don't find a border to the left, so that's not great. So you're not really reusing anything, right? I feel like this is one of those things where, like, as soon as I see something, like, or make an observation, it should be okay, but okay, it's the invariant that okay, let's say we parse the 5, right? And then what? Do we only, maybe that's the way. Maybe it's almost like a frontier thing. Can we like parse the 5? We go, okay, well, the 5s are gone because it's next to, say, infinity or whatever, or maybe negative infinity, really. Well, I guess just 0. That's fine, right? So the borders are 0, the x's, right? And then now we process the 3. Well, this 3 is next to 0, so no Gucci. We would process the 3. This is 0, so well, yeah. Then we exit all the x or the 3s, but we marking that yeah. And the reason why we do the how are we marking these, or why are we marking these other than by order? Okay, so here I see. So in a way, then now when we have 0, we have the 5s, we put in the 5s because it is surrounded by 4 numbers that are smaller than it. Okay, so then we know that because 4 numbers are smaller than it, it cannot be gotten. Okay, so now we x, right? And then now, as a result of this x, now this 3 has 2 numbers equal or smaller, and also 1 done. Sorry, 3 if you count the edge. So then now all 4 sides are done, maybe? And so you put it in, right? And as a result of this, I don't know, but then by that logic, then this 2 is also done because this number is smaller. 1 is smaller, 2 is equal, so then this is done. Then you could see yourself going this one next. That's not the way to do that. Because then now the 2 I think I'm being too complicated, because the way that I'm thinking of it is that this can only be updated. No, that's not true. If you're not careful, you definitely... Okay, let's say we keep on trying to get the smallest thing, right? But from the border. So actually we ignore the 5s. We do the 3s first, right? So we do the 3 because it's the smallest thing that is on the border. Right? So let's just say we do this one. And then now the weight of everything connects to is 3. So then it pushes a 3 here. It doesn't really update this one, obviously. Maybe not even really update this one because it can't be. but then it updates this to a 3 and push it into on the heap or something. And that number can only go down, but how many times can it go down, right? Well, it can go down by 1 a lot. Maybe, I don't know, so maybe this is a 3. And then now you do, I don't know, now you have a tiebreak and you handle this. It means that by well, no, yeah, I guess not. I guess by definition, it means that reaching this cell, even order-wise, that means that it's impossible to hit because if there was a number that could get to this number earlier, it would have gone there earlier. Yeah. In the shortest path kind of way. Okay, maybe that's right. Man, today I don't know why I'm struggling so much with this problem. The invariant is hard to say. Even though I think honestly this is really exactly what we already said about everything we said is true and kind of built toward what I'm doing now, but it's just working out the algorithm and implementation. I guess implementation is fine. We have a heap, right? It's just that I don't know how, about proving it, even just to myself, right? Yeah. So then now for x, actually. So then now we want to do like the first row, last row, right? X, well, I guess this is first column. Right, and then this is first row, right? And of course, we do it for the last row as well, right? Or something like this. I don't know. Am I on the right track? So then now you have, and this is dexterous, just to be, maybe I didn't say that keyword, if you will. Okay, so then now, yeah, maybe like a, oops. I guess technically this should be the height map. Yeah, okay, fine. Right, and then now, yeah, I mean, I guess this should set it to the thing, so that's fine. And then now, wow, and I didn't write this. Heap in Python, it's like the only thing that's not OOP, so I'm always confusing. I mean, it is OOP in the strictest definition of the word, but it doesn't have the OOP synthetic sugar. So I always forget the syntax, or just forget to type it out, not that I forget what it is, for example. But yeah, okay. So then here we have the height, x and y, right? So what does that mean? And also let me just set up the grid. Okay, right, and then now and this is standard distro stuff for now, and if the height is less than their best height. This is not right, actually. This should be infinity. I was wrong on this one, actually. I mean, it should eventually converge to that, but not yet. I was just being lazy here. And maybe this should have a helper function. It's what I need to do. And now I'm just copying and pasting, obviously, which is how people get in trouble. Hopefully, I'm not this time. Okay, right. So then now, if they're then we just set it, and then we push it. This is terrible because I use H for height and the heap. That's why I'm confused. I am a terrible boy. Right. And then now we can say if yeah. I think there is a nuance here that I'm missing. That's why I'm struggling a little bit. But okay. But I think the thing is that this should be like, you can't go uphill, right? So so this is best, or the max of height and height map of the new cell, right? So we'll queue the new cell and the new height, but that's okay because it'll be later in the heap. As long as that's the case, it should be okay, I think. Yeah, and then now it's just going through the entire thing, right? So X. And that should be what I envision it. I don't know if it's right. I think, is it fast enough? Do I have a hidden n square thing that I don't know about? Okay, no, the answer is not yet. Maybe it still is true that it is wrong, but how did I get this up? Okay, so we expected 12, we're at 14. That's good in that we're not, actually, is it? I don't know. We're overestimating it, which is not great, actually. Usually, I think at least this one in theory should be okay to debug. Maybe. So this is the input. I think this is fine. It's just that I need to print it in a more easy visualization thing. Right. Okay, so then I have this. Well, 9 is definitely not right for these. Am I putting the right thing? Oh, it's a 5x4, not a 4x4. Okay, so I was like, wait, how? That's just like really off. Okay, so the idea here is that I put 14, expected is 12. Okay, so the 8, 8, okay, so the 2, it seems like the 5 is okay there. 5 is okay for the 1, 5 is okay for the 1. 1 doesn't change. This 6 should not be a 9. This 6 should be a 7. So that's the wrong answer. This 6 is turning into a 9. Why? 9, 9. Height map didn't change. So ideally, I think my idea still should be right. Because basically going in from 9, okay, we update this to 9, but there should be a 7. Maybe we don't do that, that's why. Maybe we don't queue the 7 because of this thing. Because this is not better than, oh no, the first time it does queue the 7. That's how you get 7 for the best. But the 7 should queue a 7 here and here. Why does it not queue the 7 here? Oh, we queue the height. We don't queue this, so I think we messed up there, that's why. Okay. Very silly. This is what happens when you copy and paste instead of you missed the place where you needed to do the thing. Where my okay, it's because I need to use the walrus operator. It's very awkward every time. I don't know. I mean, maybe it is Pythonic these days because, well, they introduced it, right? So it's deliberate, but it feels awkward. I don't like the walrus operator. Okay. Honestly, this was a very hard one for me. As you can see, it took 40 minutes. I think I did have similar ideas to this earlier on, but I'm still honestly not quite sure how to prove the bounds on this one, right? I think that was why I didn't jump to this one. I don't know how to prove, yeah, like I said, I don't know how to prove the bounds for this. But, and as a result, I don't know how to do it. Like, I don't know if this is just a weak inputs, weak test cases, or weak Larry, right? Yeah. How, I mean, because you can use the usually there's an argument, you update, and it can be at most 4 values, but that's not true. So then the reason why I struggle this much is that we want to prove how many times do you unqueue something, right? I guess it can only, I want to say it still can only unqueue 4 times, even though it's not clear. I think the reason why each cell can only unqueue 4 times is because there are 4 directions, but it's because there is this monotonicity to the way we queue and update, because basically there is this like induction thing. I don't think I'm going to explain this well enough, honestly, because I'm struggling as well, right? But I think the idea here is that, okay, well, the usual argument, as we said, is for n square, right? Like if you have an n square thing, and I'm doing this in 1D again, you have this case, you update, in this case, maybe you want to update, let's say there's a 4, 3, 2, 1, well, right, 2, 3, 4, 5, and you want to update here by this update, so this 3 updates to 2, but then what if 3 later gets, you know, so, okay, let me draw some arrows. Let's say we want to update from here, and we update to this direction, right? So the 3 updates to 2. So then the problem is that maybe in the future, and this is 1D, so this is a little bit crappy, this 3 will get lower, right? Like maybe the first time it updates, it has a 10. And then in this case, maybe there's a, you know, like, well, in the general n squared case, you worry that, let's say, you know, in the cell you update a 10, this cell where the 3 is, you update it to a 10, and then the 10 will update it to 2, and then next thing, something updates the 3 to a 9, and you update it again, right? But you update the down idea again. But the thing is that that's actually not possible, because when you are ready to do this cell, it is always going to be the lowest because of this monotonicity, right? Because the way that we pop up the heap, we always get the smallest number, and that means that all the smallest number in the entire tree has already, or not tree, but graph has already been processed, right? Meaning that, okay, let's say we're currently processing 3, and I'm making up numbers, it's just a cell, right? And it's 5, right? That means that there is no way to reach from the outside to get to the 3 in a cheaper way, because if it did, we would have already parsed it, right? Is this kind of, so that is the tricky invariant that I was talking about and looking for, right? The invariant here is that when you pop an item, it is the shortest thing from the outside, so you will not update down the stream, right? And what I mean by that is that when you relax 3, it is the only time you'll relax it because it is the shortest path. And it's kind of similar to how we do the other greedies, but as a result, the invariant is that when you pop a new node, it is the cheapest it will be, right? I mean, I think that's it, really. But it's a very tricky observation, to be frank. Because then, and so why does that allow, now bounds is the answer? Well, because then now, at most, the 3 will get update. I say 4, technically even 3, because it doesn't go further, but whatever. You update 4 times, because after getting what, because this one, when this parse, it'll be the lowest it can be. This thing, when it updates, it'll be the lowest that it can be. On the bottom, whenever it updates, it'll be the lowest it can be, and so forth, right? Of course, we're using a heap, so we push 4 things to the heap. But if you have like a heap update function, then actually this is pretty much dynamic programming, in that if you're able to, in dynamic programming, always get the lowest thing. And that actually is what we were talking about earlier with the DAG and resolution and all these things, is that now it has this dynamic programming property of when we relax, that means that it's in a way, it's almost like a push DP, where you put all these ideas together about adjacent things. Like all the adjacent elements are done, so then now I can go. Or it's either that, or adjacent elements have higher value than right now, which may be infinity, right? If it just never has hit. So I guess that's the idea. is still a tricky idea, honestly. But I think that's the invariant though. Yeah. So let's go over it again. Because I think this one, at least for me, was very tricky, especially from first principles. But yeah, you just reach from the outside, and you can actually simplify this if you add like padding to the map, right? And one way that you can do is just say like times 2, or sorry, plus 2, right? So then best would be right. But then now you have, I don't know, I'm too lazy, so maybe like for row in height map, you want to say I think technically you have to write some funky things. So we'll just write a new height map, right? So new height map is equal to right? This is the new C, right? And then for x in range of length of whatever, r minus 2, for y in range of c minus 2, then now new h of, actually we should set this to 0, because that's from the outside is 0. So then x of y, or plus 1, is equal to height map of xy, right? And then now nh is equal to oh, sorry, the other way around. Height map is equal to nh, just so that we're a little bit lazy on changing the rest of the code. Then now you don't need any of this. You can actually just start from the corner. The corner, because it's a 0 0 element, or 0 element at 0 0. So then you can even just, you know, right? 0 0 0, and this is the new index, right? And then yeah. And then best 0 0, and then that should propagate the rest of the way in. Yeah, maybe that makes it a little bit easier to understand. I don't know if it does, honestly. But yeah, basically the idea is that you surround the entire thing with zeros, and then you're just trying to find the shortest path from the outside in. And yeah, and this invariant is so tough to see. Or maybe for me anyway. I mean, I don't know. Maybe it's just today, cause yeah, cause the key thing to note is that this invariant has two places, right? One is that either all his neighbors are taller than it, and so you're done anyway. You can't really go any else, or yeah, because when your neighbors are done, it means that they have the shortest path from the outside. And so it's almost like like I said, kind of like a frontier thing. But that ordering is tough to kind of figure out. But yeah, that's all I have for today. Let me know what you think. I think the proof is okay that I gave you. I mean, I don't know if it's great, but I think it's sufficient. So what's the complexity, right? Well, for each cell we pop, so this is going to be n log n, right? Because the heap has 4 times n, as we discussed, number of cells, and we just pop. Well, I mean, we pop 4 times n times, which is fine, even though we don't process it further, so that should also be good. And it wouldn't change anything anyway, even if we did, because with by the same property, this would just do a for loop, but this would never update anything by definition, right? Because you already did it with a shorter height, so none of this would update anything. So you don't. So in this case, maybe you could get away without needing this, and then later kind of eat crap for it. But for this problem, it's fine. Yeah, I don't know. But yeah, but this is n log n for the heap. N is the number of cells, which is also number of edges if you think about it, because it's just 4 times number of cells, right? Is a grid. And yeah, and that's all I have. Oh, I don't know if I went over that much, but yeah, we started the border. This will allow us to populate the border, which is why I only did it for one cell. We go up, down, left, right. For each cell, we just, the cost is that you have the height and the height map. Oh, I used nh again, didn't I? Yeah. to get the shortest path to the cell, right? Where the cost of the path is defined by the largest edge so far you've seen on this path, and then you push it to the heap, and you always get the smallest heap. And at the end, best is just the height that you can get away with, and height map is the well, that's just the starting height, and this is the highest height, and that's it. Very tricky problem. I don't know. Maybe we'll look at tutorial. How would I do it? Trapping BFS and priority queue. Where did the BFS come from? That's what I'm curious about. Otherwise, the priority queue is fine. Where's the BFS? Did I miss something? Oh, there are two. Oh no. This is basically what we were doing, but I don't see the BFS part. That's why I'm confused. And they wrote so much code. This is almost like ChatGPT code. There's so much comments, but I don't see the BFS part. That's why I'm like confused. Maybe. I don't know. All right. Well, I guess we're okay. I don't know. I mean, we did it that way, but I just wanted to see whether there is some, and the confusing part for me was just the BFS, because I don't know. It doesn't seem like that was used. Anyway, though, that is all I have for this one. Let me know what you think. Thanks for watching. Yeah, stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.